move to lecture 7, heterogeneous chemical reactions. We finished the lecture 6 is homogeneous chemical reaction, but here, heterogeneous chemical reaction means the reactions involve two phases or two or more phases of reactants and products. So first of all, we need to additional consider will be the mass transport or the heat transport between different phases of reactants or products. So here is the outline of these lectures can be simply divided into 3 parts. The first one we are going to talk about will be the fluid, solid, heterogeneous chemical reactions. And the fluid here can be the gas or the liquid. So this reaction can involve either the gas solid or liquid solid chemical reactions. And the solid here, we will put more efforts on the materials, the material with flat interface or flat surface. For example, like oxidation of the silicon substrate. So we can ask by using, as long as we learn how to get the overall rate equation for the fluid solid chemical reaction, then we can estimate the thickness of the oxide layer grow on the silicon substrate. And the second part we are going to talk about will be the fluid chemical reactions. So fluid chemical reaction usually can be discussed will be the gas versus liquid or two insoluble liquids chemical reactions. And no matter is the fluid solid or fluid chemical reactions, we are going to introduce you a new concept we call transport resistance and reaction resistance. What this means, as you know, for in heterogeneous chemical reaction, we need to consider the time spent allow the reactants be transport to arrive the surface of the other reactants. Okay, so it definitely spends some time for transport, then we'll have the chemical reactions. So it can be a full story transport, then reactions. So it considers a series of reaction, right? So in order to quantitatively describe how much time is spent in transport and how much time is spent in reactions, so we use the term called transport resistance and reaction resistance to describe it. So as you know, as you learn from the electrical circuit, resistance means what? If we have a higher transport resistance, means this atom, this molecule or this reactance is not easy be transport, right? The transport rate is low. So if you have a higher transport resistance, means the transport velocity is slow. And also, if you have a higher reaction resistance, that means the reaction rate is slow. Okay, so actually you just have this roughly pictures for resistance. Then this is, as long as you have this resistance, we are going to try to show you how to get the overall rate equations, including the transport and reactions. And the third section we are going to talk about will be a fluid particle chemical reaction. The particle also solid, but with different diameters. So here, in these sections, we are put more efforts on the particle size effect. How this size affects the overall rate equation. So here we are going to introduce you two different models. The first one we call it is a congressive conversion, and the second one we call the shrinking cone models. So here we are going to tell you how to calculate or determine the rate limited step, and also the overall rate equations. So let's move to and put more emphasis on the size, how the size of the particle changes as a function of reaction time. Okay, so let's move to the first part is the fluid-solid chemical reactions. So before we move to how to really calculate or estimate the overall rate equation for fluid-solid chemical reactions, we want to show you the applications. The important applications is you have chance to estimate the thickness of the oxide layer grow on the silicon substrate. So as we know, this is the fabrication process for most structures. And as you know, that's a very important layer we call the oxide or gate oxide layer here to insulate the gate with the drain and source. It will be serving an insulating layer. And the gate oxide layer is very important when you fabricate this device, right? So how to choose the fabrication method to have a fast growth rate is important in semiconductor industry. So in order to estimate the thickness of this oxide layer, to grow the oxide layer, you need to know how to calculate the growth rate, right? And as you know, the growth rate for grow silicon oxide involve either the two normally commonly see is you can use the dry method or the wet method. For the dry method is you use the oxygen react with silicon substrate, then you can get an oxide layer. So oxygen react with silicon substrate. So it's also the fluid-solid chemical reaction. The other one is the wet method is using the water vapor react with silicon substrate, also involve the fluid-solid chemical reaction. So in order to know which method, dry or wet method, can help us to have a higher growth rate to grow the oxide layer, then we need to know how to estimate the growth rate here. So before show you how to get that, we need to have some basic definition for heterogeneous chemical reactions. So what's the heterogeneous chemical reactions? When more than one phase, can be the two phases or more, is presented in the systems. So the overall equation you need to consider the phase-to-phase mass transport and the chemical reaction kinetics. Both these two items to have then you can get the overall rate equation for this heterogeneous chemical reaction. So here I'm going to give you an example is the solid carbon react with oxygen, then we can generate a carbon dioxide in gas phase. So when you try to draw the reaction, so we have a solid carbon here, and oxygen will exist presented here. So if you want to consider the overall rate equation for this heterogeneous reactions, you need to consider what the oxygen molecules need to be transported to arrive the surface of the solid carbon, right? So this between the gas and the solid phase, we call it is a thin layer, or inside this layer, the molecules be transported, so diffuse through this layer. So the oxygen was transported or diffused through this film layer to arrive the surface of the solid carbon. So the first one is the step will be the mass transport of oxygen to the surface of the particle inside the film layer. Then will allow this oxygen molecule react with the carbon. Then that will generate the carbon dioxide. So the mass transport of carbon dioxide out of the surface of the particle. So you can consider this heterogeneous reaction involve these three parts. And these three parts belongs to series reactions. And in order to simplify this kind of heterogeneous chemical reactions, usually we will assume the products carbon dioxide can easily go out of the surface. So this reaction will always the reaction direction of these reactions will always go to the right-handed side. Otherwise, based on the Ch7 principle, if you put the system into the container, then the concentration of carbon dioxide increase. Then they will have chance to reverse these chemical reactions. So in order to simplify all these reactions, we just assume the products. For example, like this carbon dioxide can easily go out of the surface of the carbon. So that will allow this reaction always go to the right-handed side. So now this is easy, right? Because it definitely carbon dioxide will leave the surface. So in order to consider the overall rate equation, we need to consider mass transport part and reaction part. And the relationship between this will belongs to series reaction. So how to model this kind of heterogeneous reactions, including the transport and the reaction? What you learn in the electrical circuit is you can apply you can put in the battery to apply the voltage on the circuit. Then you will observe the current be generated passing through all electronic device with resistance, right? So V equals to IR is how you get or learn from electrical circuit. So here you can use the same idea to model the overall heterogeneous chemical reactions. So for example, like the V here is a driving force, right? So the driving force here for this reaction, actually you can consider as what is the concentration gradient of the reactant. Here is the concentration gradient of the oxygen. Because we have a sufficient oxygen here, and oxygen will diffuse through the film layer, then arrive on the surface of solid carbon, right? Then that will start the chemical reaction. And if we can assume that the oxygen be completely consumed out. So the concentration of oxygen will drop to 0. So from here to here, you can observe there's a oxygen concentration gradient and serving a driving force to allow the oxygen can always molecular can always diffuse into this film layer, then react with carbon continually, right? So this concentration gradient of oxygen serving a driving force. And what's this is I, right? Is a current passing through the circuit. So what parameters similar to current passing through this heterogeneous reaction? Here you can consider is a flux of the oxygen. Because of flux of oxygen, when it reaches steady state, that means how much oxygen flux flow through this film layer will be equals to how much flux of oxygen react with carbon, right? So the flux, when it reaches steady state, the supply of oxygen equals to consumption of the oxygen, right? So this double prong is the flux, and double prong if you check the definition from lecture 6, it means the consumption rate of reactants per interfacial area, because the reaction region in this case actually is a surface of the solid carbon or interfacial surface of the solid carbon. So we use a double prong too. So it's a per interfacial area. And the resistance here in the electrical circuit actually is corresponding to resistance for each electronic part. But here you can consider as a transport resistance and reaction resistance. So now we use the same idea to find out the driving force, the flux passing through whole different resistance. So this is how we model the overall heterogeneous chemical reactions. So let's give you a real example here. This just hope you can have a picture, okay? So here we are going to derive and show you, yes, these results definitely can, by using this electrical circuit, the way we just introduced you really can model and also integrate or incorporate the mass transport and reaction parts in this whole circuit. So the example here we give to you is a liquid-solid reactions. So we have the liquid A react with solid B, then we generate liquid R. So we have a liquid main body A here, and this is a solid B. And also it have chance to generate the liquid R. In order to simplify this heterogeneous reaction, we always assume that the product R can easily leave the surface of the solid B, so allow the reaction direction is always all the way to the right. So it's an irreversible reactions. So have a look, we use the blue curve to plot the concentration of reactant A. So inside the liquid main body, we know the concentration of Ca is uniform. But as you know, the A is going to diffuse through the film layer. Here, the film layer we call it, if the film layer is between the liquid and solid, we call it as a liquid film layer. So the A is going to diffuse through this liquid film layer to arrive the surface of a solid B and react with solid B. And we assume after chemical reaction, the concentration of reactant A will be equals to 0. We assume it is a complete consumption chemical reaction. We are going to completely consume the reactant A at the surface of the solid B. And here, I remark here is if less because the liquid A is diffused through the liquid film, right? So it obeys the fixed first law. We assume it obeys fixed first law, so concentration will decrease with the distance. But as you know, if the concentration is, if the profile is like a flat, that means there's no resistance, no transport resistance in the liquid film. But as you know, because the kinetics model inside the liquid film, definitely reactant A is diffused through film layer, so that must concentration gradient presented in the film layer. And now, if it is reached steady state, then we can find the flux of reactant A inside the film layer will be equals to the flux of reactant A consumed in the chemical reaction. So JAL inside the liquid film transport, how much A be transport inside the liquid film will be equals to how much A B react with B. So now we use this to formulate, we try to get the flux. So here, for the flux of reactant A diffuse into this film layer, we can use the minus R double prong AL. A is reactant A in the liquid film layer. Then we use the consumption rate of reactant A per area, per unit area S. So the behavior of reactant A is diffused through the liquid film, right? So need to obey the fixed first law will be minus diffusivity concentration gradient. And concentration gradient we use is CAS minus CAL over the thickness of a liquid film. And here, some people will also use this diffusivity over delta X. Use the term we call the KL is a transport coefficient of this liquid film layer. And this coefficient is related with the diffusivity. The diffusivity here is a reactant A diffused into the liquid film. The diffusivity of reactant A diffused into a liquid film. So if you have the higher transport coefficient, means the diffusivity is higher. That means transport faster. So as you know, the transport coefficient means if you got the higher transport coefficient, means the transport is fast. And next, we are going to try to formula the JR, the reaction rate, and also express as a consumption rate per interfacial area, because the reaction only happens at the interface of liquid film and solid, because this is solid, so the molecular bead is not going to jump out or go out of the surface, right? So we also use the per interfacial area, and we assume it is so double prong is per interfacial area, reaction area. We assume it is a first order reaction, so K double prong CAS, because the concentration at the surface of a solid bead is CAS. Okay, so when it reaches steady state, that means the supply of reactant A will be equal to consumption of reactant A, so equals, right? So you can use this. You can, because this equals to this, so you can get the CAS as a function of CAL. Why are we going to use this one? Because it's very difficult to us to formulate, to get the rate equation expressed like as a function of CAS, because what is CAS? Is a concentration of reactant A at the surface of solid bead. It's very difficult to measure CAS. Instead of CAS, if we can express this value as CAL, then CAL is easy to measure. So we are going to substitute the CAS as a CAL here. So by eliminating the unmeasurable CAS, the rate equation can become this, and just use this to substitute this one. So you got this one, and you divided K double prong and KL together, so you will get this one, this results. So the rate equation, the consumption rate of reactant A, can express like this. And CAL, what's a CAL? Is a concentration of reactant A in the liquid main body, right? And the bottom part, we find the reciprocal of KL, reciprocal of transport coefficient, and reciprocal of rate coefficient. As we know, the higher transport coefficient means what? Means transport faster. Reciprocal of the transport coefficient is the resistance. If you transport faster, means the resistance is small, so you use the reciprocal of the transport coefficient. And same idea of if you have a higher rate constant, means react faster, right? Reciprocal of rate constant, you got the resistance of the chemical reactions. So this is the results. So let's check. If you consider a circuit, electrical circuit, then usually you have the voltage drive this current, right? Passing through different resistance. So here, as we mentioned before, CAL, because finally we consume, at the service the reactant A be consumed completely. So it's a CAL minus 0 serving a driving force. So it's a V. I is a flux because the flux alone passing through the resistance are the same, right? So flux V I R, and this is the total resistance, including the transport and also the chemical reactions. So some people will also write it down like the driving force CAL minus 0, and this is the flux and also the overall resistance, including the mass transport and reactions. So, okay. So here we successfully to show you when you can easily to write down the rate equation for this liquid solid reactions, consumption rate equation, by the idea with I just show you is the driving force is a concentration gradient, and the consumption rate actually is a flux, right? So it's a driving force flux passing through whole resistance, and the resistance included is a series reaction included the mass transport and also reactions. And so in your experiments, we know the CAL, right? And you also, as long as you measure the consumption rate of reactant A, and you have chance to reformulate these reactions, right? Reconstruct these reactions. As long as what? So either you can, because we know this value, so probably you have chance to know what's the KL and K double prime by the method we just show you in the you can know the K double prime as long as you know the K double prime and KL is related to diffusivity and delta X. Then you can successfully to know the consumption of reactant A. Okay, so you can reconstruct. You can know the you can construct this overall rate equation. Okay, so today we just ended here.